Good morning, class. We are looking at Chapter 2, Limits, Section 2.1, Limits of Sequences. Limits of sequences. So in Chapter 2, we cover limits of sequences, limits of functions at infinity, limits of functions at finite numbers, limits, algebraic methods. First, recall, what did we cover? 1.6 sequences and difference equations. A sequence is a list of numbers written in a specific order, a sub 1, a sub 2, all the way to a sub n, first, second, and nth term of a sequence. A sub n is the general term, and n is the set of positive numbers or integers. Positive numbers, natural numbers, if you will. Recursive sequence, also known as difference equation. The format is a sub n plus 1 is f of a sub n, which means the next term depends on knowing the previous one or previous ones. An example is Fibonacci sequence where f sub 1 is 1, f sub 2 is 1, f sub n is f sub n minus 1 plus f sub n minus 2 for n larger than or equal to 3. Therefore, we get 1, 1, 2, 3, 5, 8, 13, 21. You just simply add them up. Another one was arithmetic sequence. A sub 1, a sub 1 plus d, a sub 1 plus 2d, and so on, where recursively a sub n plus 1 is a sub n plus d, explicitly a sub n equals a sub 1 plus n minus 1d. The next one is geometric sequence, where you have a sub 1 times r, a sub 1 r squared, a sub 1 r to the power of n minus 1. Therefore, recursively, a sub n plus 1 is r a sub n, explicitly a sub n equals a sub 1 r to the power of n minus 1. And now 2.1, limits of sequences. Here's the summary of what is coming up. Limit refers to the long run, long-term behavior of a sequence, i.e. what happens to a sub n of a sequence in the long run. The limit of a sub n as n approaches infinity is L. We say that a sub n converges to L. Limit of a sub n as n approaches infinity is infinity, or negative infinity, or D and E does not exist. We say the sequence diverges. And to find limits, simply plug in the value and observe. We discuss this further as we come across. So this is the summary. We're going to discuss some of the theorems. The limit of r to the power of n as n approaches infinity depends on the base. If the base r is between 0 and 1, becomes 0. If the base r is 1, is 1, 1 to the power of n. If the base r is larger than 1, this becomes larger and larger, and it tends infinite. Just to give you an idea for this one, class, if you have, for example, 1/2 and you square it, you get 1/4. If you cube it, it becomes smaller, and so forth. And that's why this thing works. And by the way, it really doesn't have to be between 0 and 1. As long as it's between -1 and 1 works that. Now let me just erase my work. The limit of 1 over n to the power of p as n approaches infinity is 0 for p being positive. Because if it's negative, it comes up. Remember the negative exponential rule. So if p is positive, as n goes to infinity, the denominator gets larger and larger. And as the denominator gets larger, the fraction gets closer and closer to 0. You remember geometric sequence and now geometric series. When we add them up in algebra, you remember the summation. This is the summation of a r to the power of n minus 1 going from 1 to n. Add them up, you get a times 1 minus r to the power of n over 1 minus r. If r is between -1 and 1, Remember, this limit goes to 0, so this goes to 0. We can replace that with 0, and we get a over 1 minus, or in other words, it becomes a number, it converges. So b sub n plus 1 is r b sub n, or b sub n equals b sub 0 r to the power of n. B sub 0 or a, depending on the text that you're dealing with, b sub n is a r to the power of n. That's the geometric sequence. And it's important to pay attention to the recursive format and explicit format. If you recall, if we go with b sub 1, we put r to the power of n minus 1. That's another way of writing it. That is the same thing if you go with that format in any event. Now, what happens, for example, in the case of patients and given in medications, what happens if we have the same thing and we have a constant? Now, the solution b sub n becomes the same thing, and then we add this factor c times 1 minus r to the power of n over 1 minus r. We discuss that as we come across it. Or we let a be equal to b sub 0, depending on the text. Let's see what happens in general. So this is the summary of what's coming up. What happens to a sub n of the following sequence? Let's calculate the first few terms. In this case, a sub n is 1 over n. So let's just plug in. If I put 1, I get 1 over 1, which is 1. If I put 2, I get 1/2. If I put 3, I put 1/3, right? If I put 10, I get 1 over 10. 1 over 10 or 0.1. It shows, just by plugging in, it is approaching 0. Therefore, the limit of 1 over n as n approaches infinity is 0. It's convergent. So basically, if I were to plug in, I would say 1 over infinity. That means 1 over a huge number is 0. So it looks like this. In general, the limit of 1 over n to the power of p, you remember that from the previous page, as n approaches infinity is 0, as long as p, the exponent, is positive, because if it's negative, it comes up. And if you were to put it into a graph, it's a discrete value. We have a bunch of points, and eventually it becomes, in essence, a horizontal asymptote. It runs along the x-axis, or in this case, the n-axis. What about here? Let's plug in 1. If I plug in 1, I get -1. If I plug in 2, I get +1, because -1 quantity squared. If I put 3, I get -1. If I put 4, I get +1. So as it appears, it's -1, +1, -1, +1. It alternates, it oscillates between -1 and 1. And therefore, the limit dne does not exist. B sub n is divergent. When you can pinpoint a number, it's convergent. When you can't, it's divergent. If you were to graph it, it looks like that, okay? It oscillates between the two numbers. Sequential limits, a sequence A sub n has a limit L, and we write, let A sub 1, A sub 2, A sub all the way n be a sequence and L be a real number. We write the limit of A sub n as n approaches infinity is L if we can make A sub n arbitrarily close to L for all n sufficiently large. We also say that A sub n converges to L. This is the definition. Now, these are limit laws. If A sub n and B sub n are convergent sequences and C some number is a constant, Then the limit of the sum is the sum of the limits. Limit of a7 plus b7 as n approaches infinity is limit of a7 as n approaches infinity plus limit of b7 as n approaches infinity. Then the difference is the difference of limits. If you have a constant you multiplied, you can take it out. If you're multiplying two of them, you can do them individually. The limit of a constant doesn't change no matter what happens to n because it's independent of n. And the limit of the ratio is the ratio of the limits, and then so on. We say, again, reminding you of the limit of 1 over n to the power of p as n approaches infinity is 0, as long as p, and that's the key, p is positive. So we write the limit of a7 as n approaches infinity is infinity if we can make a sub n arbitrarily large for all n sufficiently large. Finally, we write the limit of a sub n as n approaches infinity is negative infinity if we can make a sub n arbitrarily negative for all n sufficiently large. And of course, the sequences diverge in the last two cases. So over here, they diverge. Let's make some sense out of this by looking at a couple of simple examples. We know this to be true. We want to find the limit of 2 to the power of n minus 1 over 6 to the power of n as n approaches infinity. This is a warm-up example. How do we come up with the answer? So we separate it into two pieces. This one is 2 to the power of n over 6 to the power of n, and this is minus 1 over 6 to the power of n. So this would be the methodology to come up with the answer. Now, as you can see, this one is 2 over 6. That means 1/3 to the power of n. This one, class, whether you have 1 or 1 to the power of n makes no difference. You can say 1 over 6 to the power of n. According to the limit laws, we can separate them. The limit of the difference is the difference of the limits. So take the limit of this piece, take the limit of this piece, and subtract them. What is this limit equal to? The limit of 1/3 to the power of n as n approaches infinity. What is this limit? The limit of 1/6 to the power of n as n approaches infinity. This follows this part. This number as well as this number, both of them are between 0 and 1. So using that, we get to 0 for each part. The answer is 0. So a quick recap. We are given this. We cut it into two fractions. We simplify this into 1/3 to the power of n. This one 1/6 to the power of n. We cut it into two limits, and we use the theorem. All right, example one, finding sequential limits, reminding everybody of that, and a to the power minus m is 1 over 8 to the power of m. So let's start with this. Just plug in. To find limits, simply plug in. So if I plug in, I get 2 to the power of infinity. The limit of r to the power of n as n approaches infinity is infinity if r is larger than 1. So if this number is larger than 1, any number, 2 to the power of infinity is infinity, which if they ask, it means it diverges. Same thing here, plug in. When we plug in, We're going to remind everybody a to the power of minus m is 1 over a to the power of m, which means this part is 1 over 2 to the power of infinity, or 1 over infinity, or 0. So the answer is 5, and it converges. Plug it. 1 plus 1 over infinity. 1 over infinity, we should know 0. Or you can even use this theorem for that. And the answer is 1. Therefore, we say it converges. Find the limit of 2n squared plus 3n minus 1 over 5n squared minus n plus 8 as n approaches infinity. So what is the technique involved? Now we want to discuss techniques. If you have a rational expression and the variable nx is approaching infinity, the technique is to divide by highest degree in the denominator. So we are going to divide everything by n squared. One more time. If you have a rational expression and the variable is approaching infinity, x, n, whatever, then you divide by highest degree term in the denominator. By the way, division by n squared is the same as multiplication by 1 over n squared. Doesn't matter. I just wanted you to be exposed to both. So the limit as n approaches infinity, this one becomes 2. This one, 3 over n. This one, minus 1 over n squared. This one becomes 5. This one, minus 1 over n. This one, 8 over n squared. Divide everything by n squared. Because n is approaching infinity, if we plug in infinity, this goes to 0, this goes to 0, this goes to 0, this goes to 0, and you get 2 over 5. And we are done. So a quick recap, the technique is when you're dealing with a rational expression and the variable approaches infinity is to divide by highest degree term in the denominator. Let's look at this example. And again, we have a rational expression. We divide the top and the bottom by highest degree term in the denominator, which is n squared again. And we observe. So what happens? This becomes 3 over n. This becomes minus 1 over n squared. This becomes 7. This becomes minus 3 over n. Now, obviously, this goes to 0, this goes to 0, this goes to 0, but 7 remains. It's important to know, I want to explain this. What you have here is 0 over 7, and 0 over 7 is 0, because sometimes we come across 0 over 0, which is indeterminate. We don't want to mix them up. And I hope you remember when we did horizontal asymptotes in pre-calculus, we said when the degree of the numerator is the same as the degree of the denominator, y equals 2 over 5 is the horizontal asymptote. When the degree of the numerator is less, becomes 0. And if it's larger, as it is the case here, we're going to again divide by highest degree term in the denominator n. And let's observe what happens. So divide everything by n. So this becomes n, this becomes 2 minus 1 over n, and keep the limit. Remember, we are not losing the limit until we replace the n. So if you replace the n with infinity, this becomes infinity, this becomes 2, this becomes 0. And infinity over 2 or infinity times 2 or infinity divided by 10,000 makes no difference. It is still infinity because infinity is a concept. It's not a specific number, everybody. And again, reminding you that previously when you were dealing with horizontal asymptotes in algebra or in calculus, they said, how do you find asymptotes? You look at the degree, right? If the degree are the same, the leading coefficients take over. If the degree of the numerator is less, you end up with 0. And if it's larger than that, you don't have it. If the difference is exactly 1, you have oblique asymptote. But that's information from algebra. Calculate the first 8 terms and find the limit. A sub 1 is 2, a sub n plus 1 is 1 minus 1/3 a sub. All right, so we have the first term. Now, if I want the second term, that means this is 2, n plus 1 is 2, and n is 1. So a sub 2 is 1 minus 1/3 a sub. We've done this stuff. That shouldn't be a big deal. So a sub 2 is 1 minus 1/3 times 2. Now this is 2/3 subtracted from 1 and you get 1/3. In other words, I'm showing you how to come up with the answer very easily. And of course, you can do that. And by the way, 1/3, if you want to go with the decimal notation, would be 0.3 bar. According to this formula, if I want this to be 3, that means a sub 3, n plus 1 is 3, n is 2, so this is 2. A sub 3 is 1 minus 1/3 a sub 2. In other words, if you want a term, any term, pick 1/3 of the previous one and subtract from it. So 1 minus 1/3 of that. As you know, 1/3 of 1/3 is 1 over 9. So 1 minus 1 over 9 is 8 over 9. So we can continue and get the rest of them. I'm assuming nobody has any problem with the rest of them. So we got the 2 of them. We can find the rest of them in the same manner. And then eventually, if you continue towards the end, you see that there's not a lot of changes, and that becomes the limit if it converges, unless it oscillates or it goes towards infinity. So you'll see what happens. Now, what I want to tell you for a case like this, if it becomes tedious, you can use a graphing calculator to find the rest of them. Because if you can show work for 2 of them, that means you can do the rest of them. This is for the sake of a homework, okay? And so a sub 1 is 2. You store it in x. That means storing in x. A sub n plus 1 is 1 minus 1/3 x. You store 1 minus 1/3 x in x, because that's what you have here. That means you're assuming the limit exists. So you're just saying limit is 1 minus 1/3 of the limit. The L that we used at some point, if you remember, now we're using x. Same thing. And then press enter key repeatedly. I'll show you algebraically or analytically as well in a moment. So if you store the 2 in x and then 1 minus 1/3 x into that, you get obviously 2 for this one, and this one will give you this number. Remember, this is 1/3. Do it again, gives you the next number. 8 over 9 is 0.8888, and anytime you stop, you have to change it to 9. and now the rest, and you can put them here. Now, this should indicate the sequence converges to 0.75. If you have doubts, you can do a couple more, and at some point it practically stops. Okay, but I want to show you the proof with algebra analytically by setting them equal and solving them. Okay, so if the two are equal, as it's given here, then when I take the limit when n approaches infinity, they are also equal. So what are they equal to? We're going to discuss that in a moment. So first, let's look at this one. If I use the limit laws, it's the limit of 1 as n approaches infinity minus 1/3 limit of a sub n as n approaches infinity. A constant is itself. So this is 1. Okay, and remember, we are going to assume there is a limit. So we are going to assume this has a limit and it's L. This has a limit and it's L, or X, or Y, or Z, any variable of your choice. Assume the limit exists, and the limit of a sub n plus 1 or limit of a sub n makes no, at some point, as n approaches infinity becomes L, so replace it. And I hope you see that I can move this, make it 1/3, positive 1/3 here. Make it positive 1/3. So you get 4/3 L equals 1. So I multiply both sides by 3/4. L becomes 3/4. And everybody knows 0.75 is the same as 3/4. All right, so everybody remembers the arithmetic and geometric sequence that were discussed. Okay. So arithmetic sequence, you have a constant that is being added known as a difference or distance, a sub 1, a sub 1 plus d, and so on, where the difference d between consecutive terms is constant. Recursively, a sub n plus 1 is a sub n plus d, and explicitly, a sub n is a sub 1 plus n minus 1 times d. Example 15913. Everybody remembers that. For geometric sequence, we had a sub 1, a sub 1 times r, and so on. So recursively, a sub n plus 1 is r a sub n. Explicitly, a sub n equals a sub 1 r to the power of n minus 1. 1 times 4, 4 times 4, 16 times 4, and so forth. And so if we use the first one to be a rather than a sub 1, so s sub n is the sum of the first n terms. We get a plus a times r plus a r squared all the way to a r to the power of n, and we get a times 1 minus r to the power of n over 1 minus r. And if r is between -1 and 1, this goes to 0. We get a over 1 minus r. So let's quickly look at the proof. This is what we have done in algebra. Hopefully it's coming back to us. In the case of a geometric series, we add up a geometric sequence, we call it series. So a plus ar squared, or summation of a r to the power of n minus 1, n equals 1 to infinity, a can't be 0. So if we are adding the first n terms, we call it S sub n, the first n terms. Let's multiply both sides by r. So this becomes r s sub n, this becomes ar, this becomes ar squared, this becomes ar cubed, this becomes ar to the power of n minus 1, this becomes ar to the power of n. Let's subtract this one from this one. If I subtract this from this one, okay, ar cancels out ar squared cancels out ar squared, and all the way to the end, this one cancels out this one. So what we have, s sub n minus r s sub n, is a minus a r to the power of n. Left side, we factor out s sub n, 1 minus r. The right side, we factor out a. Since we are interested in s sub n, divide by 1 minus r, and that's a proof that the sum of the first n terms, or s sub n, it stands for the sum, is a times 1 minus r to the power of n over 1 minus r. Now, if it continues indefinitely, in other words, not just n, rather n goes from 1 to infinity, then you have to take the limit of this guy as n goes to infinity, whatever it might be. If r is between -1 and 1, r to the power of n goes to 0 as n goes to infinity. And so the limit of s sub n as n goes to infinity is the limit of a times 1 minus r to the power of n over 1 minus r as n goes to infinity. You can take a over 1 minus r out, the limit of 1 minus r to the power of n as n goes to infinity. Or you can write here, say this is, you can say this is 0 here and you get 1, or you can say this is 0 and ultimately a over 1 minus r. So we prove that, and it's very straightforward, everybody. Now, let's put it to a good use. We want to add these terms, 1/2 plus 1/4 plus 1/8 and so forth. And we recognize it as a geometric sequence since we are adding them up, geometric series where we have the first term 1/2, or happen to be 1/2 also, because 1/2 times 1/2 is 1/4. 1/4 times 1/2 is 1/8. 1/8 times 1/2 is 1 over 16. So both of them, A and R, are both 1/2. And because R is between -1 and -1, -1 and +1, and it says A over 1 minus R. Plug in. This is also 1/2, so 1/2 over 1/2 is 1. So it's fascinating. If you pick 1/2 and add half of it again and again and again, the total ultimately becomes a convergent number, which is 1. Express 0.46 bar as a rational number. And you may remember doing this using algebra. There is a methodology in algebra. Specifically, we want to use geometric series here. So we know this means 0.46 and keep on repeating 46, 46, 46. That's the meaning of it. So this part is 0.46 or 46 over 100. This part is 46 over 10,000 or 100 squared, or 0.0046. And this part 0.000046. So we should recognize them either as a fraction Again, look at just the first part. As a fraction, 46 over 100 or 0.46. This one you have 2 zeros here. So recognize that. And by the way, I don't want to simplify this on purpose, okay? What I want you to recognize now, this is being added. So we are dealing with a geometric series because the first term, A, is 46 over 100 or 0.46. And R, look at the denominator, 100, 100 squared, 100 cubed. So it's being multiplied by 100. So R is 1 over 100 or 0.01. Therefore, we can use the formula. So please understand, it's a geometric series with the first term being 0.46 or 46 over 100, or because the denominator is getting larger by a factor of 100, that means 0.01 or 1 over 100. So we are going to put A over 1 minus R. You can do it two ways. You can do it with fractions. You can also do it with decimals. Okay. Either way is fine. Now, if you do it with fractions, you just multiply the top and the bottom by 100. And the numerator is 46. Let me just, so the numerator is 46 and the denominator is 100 minus 1, 46 over 99. Of course, if it can be simplified, you should always simplify it. If you go with the decimal class, 0.46 over 1 minus 0.01, 0.99, and I hope you see you multiply the top and the bottom by 100, you get the same answer. So it's really not a big deal. Let's look at another example, 5.75 bar, and we are going to deal with it in the following manner, writing it as 5.757575. So basically, this one is 5 plus this part, and this is the part we are going to do exactly as we did in the previous page. You can write it as a fraction or as a decimal. Now, if you write it as a fraction, everybody, this is 0.75, 75 over 100. This is 0.0075 or 75 over 10,000 or 100 squared. So you write, I'm going to write both of them, okay? And this is the part we're going to figure out, and we're going to add to 5. This part, just like the previous page, is a geometric series, with this being the first term, R being the same, 1 over 100. So it's a geometric series. The first term, A, is either a fraction or a decimal. By the way, I'm not simplifying the fraction on purpose, because I want you to see what we have. Of course, it can be simplified to 3 over 4. And if that's your final answer, you must change it to 3/4. And so R is 1 over 100 or 0.01. Because R is between -1 and 1, we use this. So 5.75 bar is 5 plus 0.75 bar, which is going to use this formula now. A, 75 over 100, 1 minus R, 1 minus 1 over 100. If you want to go with the decimal, you put 0.75 there. You put 1 minus 0.01 there. We're going to do it both ways in a moment. But for now, dealing with the fraction, it's a complex fraction. The fastest way to simplify the complex fraction is to multiply by LCD, multiply the top and the bottom by 100. So this becomes 75. This becomes 100 minus 1. I showed that in the previous page. So this becomes 75. This becomes 100 minus 1 or 99. So 5 and 75 over 99. Just this part, so I want you to see that if you look at the decimal, you would put 0.75 over 1 minus 0.01 is 0.99, and this is identical to this, okay? Needless to say, every fraction must be put in its lowest term. Both of these numbers are divisible by 3, becomes 25 over 33. Now, in some cases, they may not accept this as the answer. Then you have to multiply 5 by 33, add it to 25, and write it as 190 over 33. This is absolutely perfect as far as I'm concerned. It's a mixed number. But if they don't want it in that format as a mixed number, 5 times 33 plus 25 is the numerator. Everybody knows that. That's an improper fraction. Recursion for medication. What happens in the case of a medication? Let's start with the example. B sub n is 3 times to the power of n. N is 0, 1, 2. And so plug in 0. If I plug in 0, 2 to the power of 0 is 1. So I get 3. If I plug in 1, I get 2 to the power of 1. 2 times 3 is 6. If I plug in 2, 2 squared is 4 times 3, 12, and so on. So the recursive form is B sub n plus 1 is R B sub n, which means R is 2, 2B sub n, A or B sub 0 is 3. Depending upon the text, they may use A or B sub 0. This is the basic geometric sequence we are familiar with. This is the recursive format. B sub n plus 1 is R B sub n. And actually, this shows the R is 2, or you can see that 3 times 2 is 6 times 2, 12 times 2, and so on. Now let's modify the geometric equation by adding a constant term c. This difference equation arises for many real-world examples, such as when a patient is given some medication on a regular basis, daily or otherwise. B sub n plus 1 is R B sub n plus a constant. So we have this one if we add a constant, where R is the percentage of drug remaining in the body. And that's important to understand what R represents. C is the fixed amount that is given to the patient on every time step on a regular basis. So whatever we give to the patient every 2 hours, every 5 hours, and so forth, which gives rise to the following formula. B sub n plus 1 is R B sub n plus C. Solution is B sub 0 R to the power of n plus C times 1 minus R to the power of n over 1 minus R. And again, we use A equals B sub 0. Let's look at a couple of simple examples to make some sense out of this. I do have the proof at the end if anybody is interested, but let's look at this simple example. Solve the difference equation. B sub n plus 1 is 0.8 B sub n plus 4, where B sub 0 is 5. And part B, find what is the limiting value. So what is given as we look at this one? When we look at this one, of course, B sub 0 or A is given, and we look at this one. Of course, B sub 0 or A is 5. That one is given. Then comparing this one, R is 0.8. C is 4. We are going to use this formula. B sub n is B sub 0 R to the power of n plus C times 1 minus R to the power of n over 1 minus R. We're going to plug in. So B sub n is B sub 0 or A, which is 5, you put 5 here, you put 0.8 instead of R, and you put 4 instead of lowercase c, the constant. Now, I want to show you how to handle this and how to simplify it for the sake of the second part, part B. So first and foremost, this is 1 minus 0.8, which is 0.2, and you put it underneath 4. So this 0.2, and this is the same as 40 over 2, making it tone. Now, please understand, if you assume 0.8 to the power of n is like x, what you have here is 5x plus 20 minus 20x. So assume this is x, okay, if that makes it easier. So you can combine these two, 5x minus 20x into minus 15x. So the answer is 20 minus 15x, or minus 15.8 to the power of it. The reason we do that, now it's ready for the last part. We are going to take the limit. So we want to find the limit, everybody. Take the limit. To take the limit, use the limit laws, and we separate them in the following manner. The limit of 20 as n approaches infinity is just 20 minus 15. Limit of 0.8 to the power of n as n approaches infinity. I'm reminding you of this, that you should know the theorem. And it indicates that this goes to 0 because 0.8 is between 0 and 1. And if you recall, between negative 1 and 1 goes to 0. So this goes to 0. So you have 20 minus 15 times 0, which is simply tone. Example 5, a patient is injected with a drug every 12 hours. This is the time step I'm talking about. Concentration will be reduced by 90% before each injection, and the new dose increases the concentration by 1.5 milligrams per milliliter. It's very important to write the given as we read the question. And this is the formula and everything else. So what do we need to know? Because the next part says C sub n plus 1 or C sub n, instead of B, we're going to use C. So B sub 0, we're going to say C sub 0 or A. Anytime you're dealing with a patient, unless otherwise mentioned, that one is 0, always, because initially the patient doesn't have any medication in the body. So B sub 0 changes to C sub 0 because of part B, or A equal to 0. What is R? Remember, concentration will be reduced by this much. So what is left in the body? 1 minus that, or 10% or 0.1. Then we need the lowercase c, the amount of constant every time increases by 1.5 milligrams or per milliliter. So C sub 0 or A is 0. R is 1 minus 0.9 or 0.1. And lowercase c is the constant amount of 1.5 milligrams per milliliter. So what is the concentration after 3 dosage? I want to go with the table and show you that if n is 1, we get, of course, 1.5. If n is a 2, remember, 10%, 0.1, 10% of this one remains. So that means you add 1.5 and then 10% of this, which is 0.15, they add up to 1.65. That's the second. What about the third one? Then again, we are adding 1.5 and then 10% of the previous one. 10% of that, 0.165 and 1.5, 1.665, and you can continue. Or you can find the expression for C sub n plus 1. To find the expression for that, I'm going to use that and change the B to C. So we are going to rewrite the same formula and change the B to C, everybody. So if C sub n plus 1 is R C sub n plus C, see, the given will help. Replace the R with 0.1. Lowercase c with 1.5. So C sub n plus 1 is 0.1 C sub n plus 1.5. And again, for example, we know C sub 1 is 1.5. You can calculate C sub 2, C sub 3, and it gives you the same. Find the formula for C sub n as function of n. We want this one. So I'm going to write this one and change the B to capital C. So C sub n is C sub 0 r to the power of n plus lowercase c. Please don't mix them up. The reason we use capital C because they said so here. Lowercase c, 1 minus r to the power of n over 1 minus r. And all you have to do, go back to the given and plug in. So replace everything. C sub 0 is always 0 when it comes to patients. So plug in. Replace the lowercase c with 1.5 or with 0.1. And here's what happens, everybody. This obviously goes to 0. This is 0.9. You put it underneath here. And this is the same as 15 over 9 or 5/3. This is what you get. And now, just for the sake of argument, if you try n equals 1, 2, 3, you get the same table that we got here. And again, we definitely write it in this format for the sake of the last step, which is finding the limit. So if you find the limit for this C sub n, okay, the limit of 5/3 1 minus 0.1 to the power of n, you may see that this is 0, so it's 5/3 times 1. But just to do the steps, let's do the limit law by writing 5/3, limit of 1 as n approaches infinity, limit of 0.1 to the power of n as n approaches infinity. Clearly, we should know this goes to 0 because 0.1 is between 0 and 1. This is 1. So simply 1 minus 0, 1 times 5/3. 5/3, and it's a good idea to write the units. Milligrams per milliliters. A doctor prescribes a 100 milligram antibiotic tablet to be taken every 8 hours. Again, 8 hours times 10. Just before each tablet is taken, 20% of the drug present in the preceding time step remains in the body. We have to pay attention to that. And before even we get on with the questions, we want to write the given first. So to write the given, everybody, when we look at part B, we see Q instead of B. So we're going to go with Q. First of all, B sub 0 becomes Q sub 0, or A is always 0. Lowercase c, 100 milligrams of antibiotic. And what remains in the body is 20%, so R is 0.2. So that is writing the given. Now, what about the third tablet? The first one is 100. The second one, 20% remains. 20%, that means 20 remains plus 100. Again, 100 plus 20% of 120 is 24. They add up to 124. It's very simple to figure this out, everybody. Write the expression for Q sub n plus 1. So we're going to use this one and change the R to Q. So we have B sub n plus 1 is R, B sub n plus C. So we're going to change it to Q. And now R is 0.2, lowercase c is 100. And you can calculate Q1, Q2, Q3 also. Okay, in the same manner. Q1 is 100. And then now Q2, 0.2, Q sub 1, and 100 and so on. Now, what about this one? Again, I'm going to go to this formula, everybody, and change the B to Q. Change the B to Q. I mean, it's just a variable that you're using. And again, see how much help we have here? The given, just plug in. You don't have to do much. Just plug in. So Q sub 0 is always 0. Lowercase c is 100, and R is 0.2. So this is obviously 0. This is 0 0.8. We put it here. We get 100 divided by 0.8, or 1000 divided by 8 is 125 times 1 minus 0.2 to the power of n. And if you try n equals 1, 2, 3, you get what you have here. Now let's take the limit of this expression, everybody. And again, I hope you see that this will result in 0, but let's use the limit laws. Take the 125 out, take the limit of 1, take the limit of the second expression, and this goes to 1, and this goes to 0 because 0.2 is between 0 and 1. So this is 1 times 25, 125. We get 125 milligrams. So the limiting value is 125. And again, what does it mean? If you keep on giving the same amount to the patient forever and ever, it never goes beyond 125, and it is safe.